Hello, my name is Guillermo Zavala, and from Pontificia Universidad Católica del Perú, and I will present the paper called Implications of Nonlinear Shear Strength and Interface Envelopes of Reinforced Compacted Sand Fields in Very High Earth Structures, a paper developed with Dr. Miguel Pando from Drexel University. As an outline of the presentation, I'll present an introduction, a couple of examples of very high mechanically stabilized earth walls and geosynthetic reinforced slopes project worldwide and in Peru. Talk about the possible implications of the very high normal stresses in MSE wall designs and GRS, and talk about the effect of high normal stresses on shear strength of the backfill and on the interface friction envelopes, and present a summary and conclusions of the paper. In the past few decades, well-established geostructures such as MSE walls and GRS, or slopes reinforced by geogrids, have been used widely, and these structures have been growing very high. So this increase in height has brought that in the bottom of these, there are very high normal stresses. So as a motivation in this paper is discuss the possible effects of these high normal stresses on the shear strength of a backfill envelope. And this topic is well researched, and you can find a lot of information in the literature. There's also a discussion of the possible effects of these high normal stresses on the backfill geosynthetic interface envelope. And this, in contrast to the other one, hasn't been really studied much. You cannot find much of this in the literature. And we'll discuss some design implications on the curvature of these envelopes. This topic idea was generated at Drexel University by the second author and their colleagues. Some of the largest or tallest MSEW and GRS projects are as follows. The support for an airport runway at Sikkim, India, where there's a mixed structure with gabion walls and then geogrid reinforced MSE wall with a total height of 80 meters, where you get normal stresses well above 1 MPa. Then other example is the runway extension at Charles Jigger Airport at West Virginia, which is a slope and one-to-one geosynthetic reinforced slope with a height of 74 meters, and also normal stresses well above 1 MPa. And this failed a few years after construction in 2015, and in 2019 it was reconstructed using a lot of different geotechnical structures like solder piles, tiebacks, liable geophone backfill, and drainage control. Now in Peru, we have most of these tall structures are at mining facilities. For example, this Cerro Verde copper mine primary crusher in Cusco has a 34-meter MSE wall with normal stress levels up to 0.8 MPa. At Constancia mine primary crusher, there's a 30-meter MSE wall with normal stress levels also at 0.8 MPa, and both of these support like 610 and 400 ton mining trucks. So these are not that tall, but they have a lot of load at the top. So that's why they have very high normal stresses in the bottom. Then we have Toquepala mine primary crusher in Tacna, which is a 28-meter MSE wall. And different project is a Pampa Verde waste dam expansion in Cajamarca, which used to be had an original dike that had two MSE, a lower and upper MSE wall. But then when they had to extend it, because at the top there was an unreinforced slope, they had to make a whole structure around it, and it was composed by a 41-meter geogrid reinforced slope. Now, what are the possible implications of these very high normal stresses in the design? Now we have at the bottom, we have these stresses that can reach up to or be more than 1 MPa. And in this design, we have a few zones that we have to take a look. And now we're going to focus on a couple of zones. One of that is the bottom zone where we have an interface shear strength between the geosynthetic and the backfill. So we can see that we can get a normal stress of more than 1 MPa. So we're going to focus on that, and also on the backfill shear strength itself. You can see all these parts of the potential slip surface are it's where soil is just frictioning against itself. Well, when we're talking about the granular backfill, here's a classical study from Lee and Seed. There have been other studies like the one in Clough and Basic, or Basic and Clough. No, so we can see here that they got to normal stresses up to 3.9 MPa, and we can appreciate a large curvature of this stress envelope. It's 41 degrees at the beginning, but then we got this curve, and you usually can see that above 500 kPa we get these curved envelopes. And then that happens usually in the lower areas of the MSE walls and GRS. And what is usually done, because software generally needs a linear envelope, so what is usually done is getting an equivalent linear at certain level of normal stress. So then we gonna be changing this C prime and phi prime, which we'll call C fit and phi prime fit, will be changing with the normal stress. We'll get an apparent cohesion and friction angle that are not really properties of the soil, but are just artifices to capture the observed curvature. So this will be changing with a level of normal stress. That's what happens when we always need a phi and a C with a linear model. Now, in an interface friction, we can see that the typical interface tests have stresses that are much lower than the 500 kPa that we mentioned before. Here is a list of a few tests, and we see that these normal stresses barely reach less than 200 kPa. So then these really don't capture at all that curvature. No, usually you get these three normal stresses, all of them less than 200 and a lot less than 500 kPa. No, and you usually get a peak and a residual friction angle, but as I see, none of those usually capture the curvature that is expected actually. There's a usually relationship between the phi and the delta, which is the angle friction between the soil and the geosynthetics. And when you have the curvature, sometimes one of the approaches is to use that same relationship. That might work, but not 100% of the time, because the curvature is not quite the same. But it's a good approximation. Here's actually a table of an actual project in Peru, the Pampa Verde waste dump expansion that mentioned in La Zanja mine in Cajamarca, Peru, where they reached up to 800 kPa, so 0.8 MPa of normal stress. And here we can see, checking the delta second over phi prime ratio, that's getting lower, which means there's actually a curvature happening in the interface. So we can see that really happens. So then, as a summary and conclusions, we can say that very high MSCW and GRS structures are common in the world and in Peru, where I'm from, and some examples are presented. Normal stresses can reach and be a lot higher than 1 MPa. Commonly designed software assume linear strength envelope and interface strength envelopes. So then, in those cases, we recommend do equivalent linear strength envelopes that are changing with that normal stress. And a problem we have is that interface friction behavior studies are very limited for knowledge process of 1 MPa and higher, so therefore more studies are needed. And then for curved interface strength envelopes, those equivalent linear envelopes are recommended unless software is modified so it can take those nonlinear behavior. And if we neglect that, then we can get to unsafe designs, because then we are not accounting for that reduction. That line keeps growing. The linear line actually keeps growing a lot, but the real solid behavior with that curve where the strength is a little less, so we can get unsafe designs. And interface shear tests are high normal stress are recommended for large projects, important projects, and ideally should be performed using project-specific materials. Thank you a lot for listening.